Hello and welcome back. In this video we're going to learn about the mean value theorem, which is a generalization of Rolle's theorem. Looking at the picture on the right, we have a function f of x, and we have two dots on the function. So there's a dot at roughly 1, which we're going to call a, and then there's a dot at roughly 4.5-ish. We'll call that b. Probably should have picked a nicer integer there. All right, so what the mean value theorem says is that if you look at the slope of the secant line, so the slope of the line going through those two dots, then somewhere on the interval from a to b, there's got to be some place where the slope of the tangent line is equal to the slope of that secant line. Maybe that happens like right around here. If you look at the tangent line going through that point, notice that the slope of that tangent line is the same as the slope of the secant line. So the mean value theorem is saying that we have to be able to find some place along the curve where that happens, where the slope of the tangent line is equal to the slope of the secant line. Now that x value where that happens, we're going to call c. It was just like in Rolle's theorem, except in Rolle's theorem, the starting and ending function values had to be the same, but here they can be different. F of a and f of b can be different. We don't have that third condition that Rolle's theorem had. Now when we look over to the algebraic way of writing up the mean value theorem, we have f of b minus f of a over b minus a. This is talking about the slope of the secant line, which, remember, we can think about as an average rate of change. The mean value theorem says that there has to be some place where the average rate of change is equal to the instantaneous rate of change, which is what f prime of c is representing. Now there's an intuitive way of understanding the mean value theorem. Suppose you're taking a car trip, and you start your car trip at t equals a, and you end your car trip at t equals b. Well, and suppose that the function is the position function. Well, if you want to figure out what your average speed was on the trip, what you do is you take the difference in the position, so you take f of b minus f of a, divided by the change in time, which is b minus a. That gives you the slope of this secant line, which represents the average speed of your trip, from t equals a to t equals b at least. Now, what the mean value theorem says is that somewhere on your trip, you had to have been going your average speed. Let's say your average speed was 60 miles per hour. Well, the mean value theorem would say, at some point along that trip, from t equals a to t equals b, at some time c, you had to be going exactly 60 miles per hour. There's just no way around that happening. Now, sometimes you could be going a little bit faster than 60 miles per hour. Sometimes you could be going slower than 60 miles per hour. But if your average speed is 60 miles per hour, then at some point along your trip, you had to be going exactly 60 miles per hour. In other words, the instantaneous speed somewhere on your trip has to be equal to your average speed, or the slope of the tangent line has to equal the slope of the secant line. That's what the mean value theorem is saying. So intuitively that makes sense. You can't suddenly be going 50 miles per hour and suddenly jump up to be going 70 miles per hour and have those average at 60 miles per hour. Somewhere in between you had to have crossed through 60 miles per hour, right? Unless you had like an amazing car that, no, even then, at some point you had to be going exactly 60 miles per hour. All right, well, in example 3, all we're asked to do is verify that this function satisfies the hypotheses of the mean value theorem on the interval from 2 to 4. And then we're going to find all the numbers c that satisfy the conclusion of the mean value theorem, which is this average rate of change is equal to instantaneous rate of change. So not too bad. Let's first verify the hypotheses. And for the most part, we're just stating them. F is continuous on the closed interval. Meaning we can't just suddenly like teleport from one position to another position, or one speed to another speed. And then 2, F is differentiable. So we can even talk about the derivative at all of these points. So it only needs to be differentiable on the open interval. And I'll just say that both of these are because logarithms are differentiable on their domains. If we look at the domain of this logarithm, it's going to be all the x values that are greater than 1. We can even peek over and look at the graph here. It's x values greater than 1. It's the domain of our function. And our interval is from 2 to 4. So that's within the safe interval of domain values. So definitely our natural log curve is going to be continuous and differentiable on the interval from 2 to 4. So hypotheses have been verified. That was the first part, the first sentence. Now we're going to find C. So the way we're going to find C is, well, first we need to get the derivative of our function. Derivative of natural log of x minus 1 would be 1 over x minus 1. Technically times the derivative of the inside times 1, but I'm not going to write that here, even though I just did. I'm going to write it and then erase it. Okay, and now we're going to write the conclusion of the mean value theorem and figure out the values of C that make that conclusion true. So here, I'll just label, this is A and this is B. A is 2 and B is 4. So when we write f of B minus f of A over B minus A, that's what it looks like. F of 4 minus f of 2 over 4 minus 2. So this should equal f prime of C. So taking this over here, we have f of 4 is going to be natural log of 3, right? When we plug in 4 into our function, we get ln of 4 minus 1, which is ln of 3. When we plug in 2, we're going to get ln of 2 minus 1, which is 1, which is ln 1. And then on the bottom, we get 2. Now f prime of C, well, that's going to be just f prime of x, but with a C plugged in. So it'll be 1 over C minus 1. All right. Now ln 1 is 0. So now we got to just solve for C. Now we can either do a trick where we flip both sides, or if you don't like that kind of trick, you can instead just multiply the C minus 1 over to the other side. Multiply both sides by C minus 1, and then multiply both sides by 2 over natural log of 3. And the last step is add 1. Whatever your favorite path is to solving this equation. This is just one of the paths. Okay, so there's the C value, and just to double check that we're not being duped here by some C value that's outside of our interval from 2 to 4, let's calculate it, and it calculates to about 2.82. That's good. That's inside of our interval. So it checks out that our work was okay here. At least it's one way of checking that. It doesn't say for certain that our answer is correct, but at least it's in the ballpark of the right interval. Now, going and showing what this looks like. It's a little bit hard to show this on the picture, but basically we have our secant line that's going through these 2 points. And so somewhere in the interval from 2 to 4, namely at 2.82, which is right around here, you get a tangent line whose slope is equal to the secant line. Parallel lines have the same slope, just as a reminder. A late reminder, after we'd already kind of talked about that. Better late than never. All right. So that's all we're going to do for the mean value theorem. Again, it's mostly a theoretical tool that's used for proving some things in calculus. Even back to earlier packets that we had gone through, we kind of brushed through the parts that the mean value theorem is used for. But just having it in your tool belt or knowing it so that when you take future calculus classes is a good thing to have. Thanks so much for watching, and see you next time.